Here we have the graph of a parabola, and it wants us to find the equation of the quadratic. How are we going to do that? Well, there are two forms of quadratics. One is ax squared plus bx plus c. And then one is a times x minus h squared plus k. And this version makes it easy to find the roots. So if you have the roots, it's pretty easy to create that equation. And then this equation makes it easy to find the vertex and graph. So if you have the vertex, you'll want to use that equation, which is what we have. Okay. So my h is 4 and my k is -6. So I'm going to plug those in. And notice the h has a negative in front of it, but the k does not. So this would be y is equal to a times x minus 4, because h is positive 4, squared. And then k is -6. So it looks like that. Now what should I do? I need to figure out what a is. What do you know about a? Is a positive or negative? Positive. How come? Because it opens up. So anybody want to take a guess at what a is going to be? It's 3. How come? Look at this here. Over 1, up 1, 2, 3. So that is 3. Now, what if we can't really tell exactly where that is? What if it's a decimal or we're not sure? How can we figure that out? Well, if we take a times x minus 4 squared plus, minus 6, we have a second point, which gives us an x and a y. So I can plug that x in here and that y in there, and then simplify and solve for a, and that will tell us exactly where a is. So let me do it. So -3 is equal to a times 5 minus 4 squared minus 6. This becomes 1, and 1 squared is 1. So I get -3 equals 1 times a minus 6. Add the 6, and we get a equals 3. Now, if you can look at the graph and figure out what a is, great. But sometimes it's not going to be that easy, because it will be like over 1, up 3/4. And that's harder to figure out. So you would need to plug in the x and the y to find a. Let's see if I can find one of those. Nope, that one's pretty easy. Well, that one's good. So it looks to me like it's missing over 1, up 1. If we were to zoom in right there, it might hit 1, 1, but I'm not totally sure. So I'm going to have to do it the long way and see if it is in fact 1. Okay. So y equals a times x plus 4 squared minus 5. And then I'm going to plug, I'm going to plug 5 in there and -8 in there. So 5 equals a times -8 plus 4 squared minus 5. So this becomes 4, and 4 squared is 16. So, or -4, sorry. -4 squared is still 16. Okay. What? Did I do it wrong? Oh, thank you. I'm glad you're paying attention because apparently I'm not. All right, so 5 equals a times x. It's x plus 5 squared minus 4. Thank you. So I'm going to put negative 8 in here. Is that better? Yes, it is. So this is negative 3, and negative 3 squared is 9. Oh, and look at that. 9 equals 9a divided by 9. And even though it doesn't really look like it, a is in fact 1. So the equation is 1 times x plus 5 squared minus 4. And I don't even need to write that 1. Okay, can you guys handle that? All right. So each figure has the same data points. However, each figure has a different curve fitting the data. The equation for each curve is shown below. So we want to find the one that fits it the best. So all the blue dots are exactly the same. And they've given us 3 different equations. Which one seems to fit the data the best? The second one. That's pretty obvious. And then use the equation of the best fit curve to predict the speed at 7 seconds. So we've decided that this is the best one. So if we had to guess how fast the object is going at 7 seconds, then we would go over here to 7. We'd figure out where it hits the graph, and it looks like just above 50. So anyway, we'd put in whatever you thought the answer was. Get it right. Oh, plug it into the equation. They gave us the equation. Even better. Okay. So you would just plug 7 in there and there. I didn't see the equations. Somebody's on the ball today, and it's not me. Okay. All right. Average rate of change. Okay. Imagine you are going to Price, and your friend is also going to Price. And so you both start out the same speed. Your friend gets a flat tire, so you slow down. You don't stop because you don't really like him that much. You just keep driving to Price, but you drive very slowly. Your friend fixes the flat tire really quickly and then gets in the car and races to Price. And it turns out you get to Price at exactly the same time. So your speed would look something like this. You speed up, and then you're going the speed limit, and your friends gets flat tire, so you slow down, and you drive really slowly to Price. Okay, that's how fast you're going at any given time. And let's say it takes you 50 minutes to arrive at Price. Okay, well, your friend is driving the exact same speed as you, and then they get a flat tire, so they stop. And they're stopped, and they're stopped, and they're stopped, and then they speed up and they drive really fast to get to Price. Okay, so if we were to graph how far you had traveled in that same time, this is what it would look like. So that was a speed graph. Now let's do a position graph. So position graphs are a little bit harder to do. So your position is going to look like this. Okay, and this is time. And this is time, and this is distance. And this right here is 30 miles from the high school, and that's where Price is located. Okay, so you sped up, and then when your friend's tire went flat, you slowed down and you went at a slow rate all the way to Price. So your friend drives to there, and then when they stop, what's going to happen to this graph? It's just going to be flat. So it's flat, 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 flat. They fix the tire, they take off, and you guys arrive in Price at the same time. Okay? Who had a faster average speed? What? The friend? How come? How would we find the average speed? Oh, good. Let's look at it a little bit different way. We'll get to that in just a second. You are in fact right. But let's say every 10 seconds the passenger in the car wrote down the speed. Okay? So the first 10 seconds they write down the speed and they say, "Oh, we're going 15 miles an hour." And then the next 10 seconds you're going 30. Then the next 10 seconds you're going 45. The next 10 seconds you're going 60. And then 65, 65, 65. And that gets us to there. The next 10 seconds, the person in the first car slows down to 20. And then we have a whole bunch of 20s. Right? All the way to the end. So ... 20, 20, 20, 20. And then we could find the average speed by adding those all together and dividing by the number of measurements. Right? So let's say that the average speed here, and I'm just going to make this up, was 33 miles per hour. Okay? Well, what about the other car? It's going to be exactly the same until the tire goes flat, and then what's going to happen? You're going to have 0, 0, 0, 0, a whole bunch of zeros until the tire gets fixed, and then what? It's going to go to like 115, 115, 115. I don't know how fast you're driving. And how do we find the average? We add them all up, and we divide by the number of measurements, including the zeros. The zeros aren't going to affect the total, but they are going to affect the average because every zero adds 1 to the denominator. Okay? And it turns out, when we do this, the average speed is going to be exactly the same. Why? It took the exact same amount of time to travel the exact same distance. Okay, this is the tortoise and the hare problem, right? It doesn't matter how fast you go in any particular time period. If the hare takes naps and the tortoise trots slowly the entire time, if they cross the finish line at the same time, then they have traveled the same distance in the same amount of time, and those averages are going to end up being exactly the same. So even though this second car had a whole bunch of zeros, they made up for those zeros by traveling super fast for the rest of the time. Okay, and the average ends up being the same. So, do we really need to take all of these measurements to figure out the average speed? No. We only need to know two things. Alex? How far did you travel, and how long did it take you to get there? That's it. We don't need to know the shape of the graph. All we need is the total distance and the total time taken. So if some other person were to go to Price and they were to travel 33 miles per hour, then the whole time their graph would look like this, right? And the slope of that line is going to be 33 miles per hour. So those three graphs have the same average speed, even though the graphs are quite different. So if we had a different graph, oh, hold on a second. Let me go back. So how do we find that? Well, this point is 0, 0. And this point is going to be, ooh, how close can I get? So it's going to be 30 miles. And I'm going to guess 6. How long is it going to take? It's going to take 56 minutes. Nope, 54 minutes. Okay. Well, all you have to do is plug that into the slope formula. y2 minus y1 over x2 minus x1. So if I do 30 minus 0 over 54 minus 0, I get, oh, I did it backwards. I get 0.5 hours. No, I did it right. 0.55 hours times that by 60. Oh, I did it. Look at that. 33.3 minutes. What a good guess. So if you want to find the average rate of change, all you have to do is figure out when did you start the clock, when did you stop the clock, and then you just find the slope between those 2 points. And no matter what happens in between, you're going to end up with the same speed. Even, let's say that somebody's flying in an airplane, and they fly super fast, and then they decide, well, we're going to turn around, we're going to fly backwards, and then we'll fly toward Price. We flew past Price, and we flew to Salt Lake, and then we hurried back, and we came back, and we landed in Price at exactly the same time. If you were to add up all of those speeds, some of them are negative because we turned around and went the wrong direction, then that would still have the average speed of 33 miles an hour toward Price. Okay, so how do we do this problem? Well, it wants to know what is the average rate of change from 2 to 5 here. What is the average speed? Well, the average speed is just going to be the slope between there. So we have 2, -1, and then we have 5, 2, and we just plug it into the slope formula. 2 minus -1 over 5 minus 2. That gives us 3/3, which is 1. And you can see that up 1 over 1, up 1 over 1, up 1 over 1. It's just the slope. So the average rate of change is just the slope between the starting point and the ending point. Do you guys want to see another one of those? Think you have it? Okay. I made a whole problem without making a mistake. Aren't you proud of me? Okay. Here we have a quadratic that we know hits the x-axis at -4 and -3. How many quadratics are there that hit the x-axis at -4 and -3? An infinite number. So we just need to find one of them. There are an infinite number of correct answers, so let's just find one of them. In fact, we're going to find the easiest one. So in the first problem we did today, we used the equation of the vertex of a parabola. Oops. Now we're going to use standard form. how do we create a standard form equation given the roots? Good. So we know that x equals -4 and x equals -3. And we need to create factors from that. What would the factors be? X plus 4 and x plus 3. Now what? Multiply those together. And we have x squared plus 7x plus 12. Now that's not the only version. That's the one we're going to plug in. How would I create another quadratic that hits in the same place? Times the whole thing by 2. Divide the whole thing by 3. Multiply everything by -pi. As long as you do multiplication to all three terms, you're going to change the shape of the graph. So you might create this graph or this graph, but they will all have the same roots. Okay. I'm not sure they're going to do this to you, but what if one of the roots was a fraction? So this is going to be x minus 6. What's the other one going to be? You could do x minus 2/3, but then your quadratic is going to have fractions in it, and there's an easier way to do it. What factor will create a -2/3? Think about that for a second. What factor would create a -2/3? I could do x plus 2/3, but I don't want to. Well, why would there be a 3 in the bottom? Because we had a 3x. Like that. When you solve that, you would subtract 2 and then divide by 3. So x is -2/3. And then you would just multiply that out, and you'd get 3x squared. This would give you -18, and that would give you +2. So that would be the equation of the quadratic. Okay. Get to work.